Hi friends, hope you are doing well. So today I'm going to start lecture 2 on this wind turbine series, and today we are going to discuss about the flow field, which is the flow inside the stream tube. So this is a continuation of my previous lecture, which was the basic introduction to wind turbines. So let's begin. I'm Dr. Ganguly. Now we saw in the previous lecture that we could derive the continuity equation at 3 points in the stream tube. So we looked at the front. So here the expression was rho A infinity into U infinity. That's the mass flow rate in front or upstream of the rotor disc or the actuator disc. Now at the actuator disc, the quantities were rho AD and UD. So AD is the cross section, UD is the velocity. So essentially that's the mass flow rate here. And downstream in the wake, we had AW and we had UW and also we had rho. Rho remained same because we are assuming incompressible flow here, which is quite legitimate because the wind speeds are typically pretty low. They may be something like 6 to 10 meter per second, and so it's much lower than the speed of sound. Now let's take a closer look at this continuity equation and the various terms involved in it. So if we look at the dimensions of rho A and U, you will see that it's kg per meter cube. That's the dimension of density multiplied by meter square, which is the dimension of area, into meter per second, which is the dimension of velocity. And so we get here, after some cancellations take place on the meters values, we get kg per second. So that is the mass flow rate. So essentially we are saying that kg per second of air coming in far in front of the rotor disc is the same as at the rotor disc is the same as far downstream of the rotor disc, and this is true because no air is coming or going into the stream tube. So that is an assumption we are making in this particular derivation. Now what we are going to do today is we are going to come up with some derivations about what are the disk velocity and so on. So again, let us look at the actuated disk here. So like I mentioned in the previous lecture, your velocity in front is u infinity. It decreases at the actuated disk, and further down it decreases to a lower value uw. So essentially in front it is u infinity, it becomes ud at the actuated disk, and far downstream it is uw. So we can say that ud would be u infinity into 1 minus a. So a is simply a factor which we call the axial flow induction factor. So this is the change, or 1 minus a is the change which the velocity goes through because it comes from the far upstream to the rotor disc. So again we can expand this out and we get u infinity minus a u infinity, and this entire value a into u infinity is the induced flow at the disk. So if you are familiar with the helicopter nomenclature, we call this by small v, but in wind turbines we are using a into u infinity here. So this a is going to play a very important role. It's the axial flow induction factor. Sometimes people call it the inflow factor also. So if you know a, you know what's the velocity at the disk, because ud would be u infinity into 1 minus a. Now we see that the continuity equation does not tell us anything about the pressure. We need the momentum equation to get into pressure. We need the Bernoulli equation and so on. So that's what we are going to discuss today. And now if we look at the rate of change of momentum, that is going to be equal to the mass flow rate into the difference in velocity between the far wake, or between the downstream to the upstream. So that is going to be u infinity minus uw. So this is the rate of change of momentum, and you can see this dimensionally. If we were to take the mass flow rate and then multiply it with the velocity, that would be kg per second into meter per second, we are going to get essentially kg meter per second square, which is nothing but Newton. So essentially this is the force which is there. This is the rate of change of momentum. Now you know from Newton's law that is the force, that is Newton's second law will tell you that. Now, this force is also going to be the same as what is going to be generated by the pressure differential between the front and the back of the actuator disc. So remember, in front of the actuator disc you had the pressure PD plus, and behind the actuator disc you had the pressure PD minus. So if we essentially subtract these two pressures and multiply it by the cross section AD, then we are going to get this force which is acting to cause the change of momentum, and so these two numbers are going to be equal. So again, if we take the units of pressure, that's Newton per meter square, we multiply it by meter square, we would get Newton. So essentially this is also a force. So these are two ways of looking at force, and now we are going to equate it. Now the reason we are of course using AD everywhere is because we know what is AD. AD is equal to pi r square, and we know the radius of the rotor or the actuator disc, so we can very easily calculate AD. So now let's go back to our derivations and definitions. We have the rate of change of momentum, which we wrote down a couple of slides before. That was u infinity minus uw, this whole thing into rho ad ud. And like I mentioned, we take the mass flow at the rotor disc because we know ad at the rotor disc. We may not know the a out in far front, we may not know the a far behind in the wake, but we know a at the rotor disc. Also, we know that ud has been now defined in this form, so it is u infinity into 1 minus a. Now let's equate these two pressures. So we relate the pressure drop across the disc with the change in airspeed. And what I have done here is, instead of writing ud, I have written u infinity into 1 minus a. So this is the equation now which relates the pressures to the velocity, density, and so on. So this equation is going to tell us some more things about the fluid flow through the stream tube. Now, before we make any further derivations, we have to find this pressure difference. And to get this pressure difference across the actuator disc, we are going to use Bernoulli's equation. Now, one of the things is that you cannot use Bernoulli's equation between the front and the wake of the stream tube, because you are actually putting in, or rather you are subtracting energy from the rotor here. So because you are extracting this Ke by the rotor disc, the Bernoulli's equation cannot be applied across the actuator disc, but you can apply it between the front of the actuator disc and far upstream, and behind the actuator disc and far downstream. So that is what we are going to do. So this picture will tell you what's happening here. We take far in front of the actuator disc, and that's going to be the region where you have u infinity and p infinity. So essentially we can write the Bernoulli equation as half rho u infinity square plus p infinity, and then in front of the rotor disc we have again half rho ud square plus pd plus. Remember, pd plus is the pressure just in front of the rotor disc. Now the second Bernoulli equation we write between the point just behind the rotor disc and far downstream. So this comes out to be half rho w square, that's the velocity at the rotor disc, plus p infinity. Sorry, this is the velocity and the pressure far downstream, and then the term half rho ud square, that's at the rotor disc, and pd minus, that's at the rotor disc. So you are seeing what is happening here. We are essentially applying Bernoulli's equation in front of the actuator disc, and then we are applying Bernoulli's equation behind the actuator disc. So this is essentially giving us two equations, and when we subtract these two equations, we can clearly get an expression of pd plus minus pd minus, and that is going to give you half rho u infinity square minus uw square. So what happens when we subtract these two equations is that these rho ud squared terms cancel out. So I get pd plus minus pd minus on one side, and on the second side the p infinity terms cancel out. So I simply get half rho u infinity square minus uw square. So I get a nice equation which essentially relates this pressure drop to the difference in velocities between the velocity far in front of the rotor disc and far downstream of the rotor disc. So now what we do is we take this pressure differential which we have obtained from the Bernoulli's equation, and then we write down the momentum equation also. And then what I can do is I can take this PD plus minus PD minus term from the Bernoulli's equation and put it here in the momentum equation, which is what has been done here. Now after some derivations we get a very interesting result that UW is equal to 1 minus 2a into u infinity. Okay, and I'm going to show this derivation in the next slide. So here I have taken this equation here, and now you can use some of your high school algebra. So if you remember, we can first of course cut off this row here. The row is same on both sides, so that goes off. The AD is same, so that goes off, and so I get this equation here. Then remembering that a square minus b square can be written as a plus b into a minus b, I get this equation here. And then I can cut off this term u infinity minus uw from both sides, and then I get here this term here, and then I further simplify it, so I get this term here, and then expanding it out we get this term here. And so now after some simplification I can clearly write that uw is u infinity minus 2a u infinity, and so if I take the brackets here, uw becomes 1 minus 2a into u infinity. So essentially that's the velocity in the wake. So now let's look at what actually happened here and what we have obtained from our derivations. So we now know that far in front the velocity was u infinity. At the rotor disc it became u infinity into 1 minus a. So this was the loss in the velocity, and then in the wake it became 1 minus 2a into u infinity. So we can write this as half the axial speed loss in the stream tube takes place upstream, so that's in the front of the rotor disc, and then the remaining half takes place downstream, so that is the one behind the rotor disc. So we now have a very clear picture of what's happening to the velocity of the air as it is going down. So remember, the fact is that the u infinity value plays a very important role in the amount of energy you can extract from the wind turbine. And so what the wind turbine does is it sucks out some of the kinetic energy from this wind, and so the kinetic energy is going to reduce, which of course means the velocity of the air is going to reduce as it passes through the wind turbine. So let's now summarize what we learned today. We saw that the continuity, momentum and Bernoulli's equation can together be used to determine the flow field within the wind turbine stream tube. So today we have figured out that pressure is going to fall across the actuator disc, and the pressure falls further at the actuator disc, and also that velocity falls at the actuator disc and further in the wake. So this is a very important development which we have seen, and this is now something which we know, which helps us figure out how the airflow takes place through the actuator disc and so on. So today's lecture we essentially figured out the flow field, which means we now know the pressure, we now know the velocity, we of course know the density because the density never changes because we are in incompressible flow. And the next stage which is going to be is to calculate the power generated and the thrust generated, because one of the fundamental principles in wind turbine design is to know how much power we can extract from a wind turbine given its radius. So again, the basic design parameter here is AD. AD is the cross section or the area of the rotor disc or the actuator disc, and if we want to design that and get some ideas about how to maximize the power produced by the wind turbine, then we are going to take advantage of these equations and come up with the derivation of power in the next lecture. Now if you are not following any of this content, I would suggest that you look at my aerodynamics playlist, which explains some of the basic equations in slightly more detail, and then you should be able to follow this lecture very well. So I will end this video now and I will see you in a video sometime soon. See you then.